Dear students, welcome to our next lecture for Cooperative Communication Systems. Today we would like to talk about green mobile clouds, and the idea is here to look into the gains that you will get if you cooperate. And we start with a very analytical model and later add a little bit of realistic factors such as mobility, and also look into a certain example that we always have discussed, the reliable cooperative multicast. So let's start first with the analytical view on the green mobile clouds. And first I will motivate this a little bit, then look into different cooperative strategies. And then one of them is a cooperative download. We'll start with this. And there you will see that we have different assumptions how this cooperative download can take place as a sequential fact, or will this happen in parallel? And then we have to understand what is the difference if the short range technology is very fast versus not so fast, and what this means you will see in a minute. So let us start with the motivation, right? We said if we would be a non-cooperative user and we would take the resources like energy, the time to download something, and the network usage, then you could compare this with a cooperative cluster. I think this should be clear by now. So when I'm cooperating here with a lot of devices, I should see a gain in energy, right? The other things I will not discuss today, but we always assumed in the first lectures that there is a gain. So how is this gain? Can this gain be calculated, and why is there a gain? That's important. Important also from our last lecture, this plot, to say what is the energy per bit over the bit rate, and you see higher bit rates will give you also a better energy per bit ratio. This has to do with the fixed cost of a radio front-end device, but I will not go into detail, just that you remember this from our last lectures. And also from our last lecture, you saw 4 different forms of cooperation. And today, this lecture is only about the technology enabled. So what we would like to do is to let the users see that if they cooperate, they have a gain in the energy. And there's nothing about socially enabled. We don't force anybody, or we don't ask for family membership. Here it's really that we want to create a technology-based cooperative behavior. So when you have different cooperative strategies, how will they look like? On the one end, we have the energy consumption for standalone device. This is always our comparison. And then we say, when we have these mobile clouds, the cooperative clusters, we have one way of streaming content. So think about Netflix and others, and to download the content. And if you download, then how do you really do this? This can be done in a strictly sequential exchange, which means we will use the cellular for a short time and then later the short range communication. So sequentially, that means when we use the one, the other will be switched off. And parallel means that we have both air interfaces continuously on. So this is where most people would say, if you have 2 air interfaces on, how can you gain in energy? And then it's interesting that in order to calculate the gains, you need to understand how fast is your short range compared to the cellular. And therefore we call this fast short range and slow short range technology. And all of these things we have to look at. So have this in mind when we go through the examples, that you don't get confused in one way or the other. Now, I would start with a cooperative download. And the idea here is to say we have a content on a server, and these are 4 different pieces. You see the puzzles here: blue, red, green, and yellow, and we convey them now over a wireless cellular network to the users. And the assumption is that everybody can see everybody, so there will be a phase where we receive from the cellular system, and then a phase in the short range where we can exchange this, right? It's a very ideal situation, as you will see later, but we have to start somewhere, and we have to also make our equations based on something. So the first thing is a cooperative download with sequential local exchange. I already said what I mean by that, but just that you understand it again. The base station here will send the 4 different pieces to the users individually. So think about an LTE channel, a PDC context where you have a dedicated channel and everybody gets one piece of the overall content where everybody is interested in, right? And what will happen then is, for example, the blue guy, after receiving his part over the cellular, he can send it out on the short range. While in parallel, all the others would receive over the short range the piece that they did not get over the cellular, but the blue guy did. And after that, the red guy will do the same. He will send it out, the others listen, then the yellow will do it, and then the green one. So you see here that two things. While one of the air interfaces is on, the others can be switched off. This is very good for power or energy saving strategies. The other thing is you will take a while, right? But you always have to keep in mind, if you would download in a standalone, you would not only get 1/4 of it, you have to do it many times. The question now is the short range exchange faster than receiving 4 of the pieces by yourself or not? This has actually to do with the rate, of course, of the short range, but it also has to do something with the coordination of this cluster. So here we strictly said how they would exchange it, right? This is very optimistic. And the cost for keeping up a cooperative cluster is also something you should always have in mind. Now, if we look into the energy consumption, so the overall energy that we would use if we would be a standalone user, we would have a power level for the cellular, and we would receive for a certain time TC, right? And we compare this energy later with a cooperative case divided by this case of a standalone user. So just to make it clear, here's the energy for the non-cooperative case. This is the power level when you receive, right? Because this is the only thing you do. And then the time needed for a certain activity. We call it TC at the moment, cellular. Now, if I do the sequential case, I would say, okay, now I will also put some energy into receiving something with the same power level, most likely. Why should this change? With a different timer, T partial, for example. So we assume that this one is shorter, right? And how much shorter? That's quite easy. If you look at the picture, you see here that we have this partial time, and this partial time is exactly, very easy, 1 over J. So J is the number of cooperative users, and then compared to TC, because TC would be the time when you would really download all 4 pieces, one after another, over the cellular link. So it's more or less the same as before. If you would divide it, then you would see, oh, there's already a gain, right? We can calculate it, but not so fast, because here this is only the cellular part. We also have to look into the exchange later. So let's look into the energy the guy will need to send. So you have here the energy, a sequential, the sequential case, cooperation, short range sending is the time you're sending in short range and the power level you will use for sending in the short range technology. So here you have to see which kind of technology you're using. It's not related anyhow to the power level of the cellular. And you will see it happens for every device only once. That's okay. So we are then saying, okay, the energy for the sending is something like 1 over JZ multiplied TC P short range sending. I think 1 over JTC is clear, right? Because it's only a part of it, right? And Z, what is Z? Z in this case is a factor how much faster the short range is over the cellular. If it's slower, then it becomes smaller than 1. But if it's Z is larger than 1, then you will say short range is faster by a certain factor. I just give you here the explanation if you look at it at home. So the power level for short range reception, this is a technical detail you can look up in the technical specs. J is still the same as before, number of cooperative users, and Z is a factor how much faster the short range is over the cellular in data rate. Good. And if you do receiving, what would you now assume for the receiving? Okay, you have also a time that you have to receive and at a power level for receiving. And the power level for sending and receiving does not have to be the same. Actually, I never found it where it's the same. You always will find different values for this if you look into certain different devices. And you see already by this picture that the time that you need for receiving is, in this case, 3 times larger than the sending, right? So how will this term change? You could maybe easily derive that it will have more or less the same parts over here, but there must be something different here because it's not only 1, it's 3 times. So maybe 3 over jz in this example, but to make it more general, we will say we have not 3, we have j minus 1 devices sending. And therefore it's j minus 1 over jz multiplied tc and the power level for short range receiving. So with that, you can do the first comparison. You can say the energy I need in the cooperative case for sequential, it's a part of the cellular, then sending on the short range and receiving on the short range. And you see here, this is the overall equation for that. I just put it in what we derived before that. And if you look at the gain and you divide the energy for cooperation by the energy of the cellular, which was TC multiplied the power for cellular reception. If you divide it here all the time, then you will see that the TC is not playing a bigger role, right? So this is nice. And what you also see that the energy here depends only on certain characteristics. One is the number of cooperative users, and the other values, like the P values here, or the Z, also the Z value here and here, these are technical parameters given by the technology. So Bluetooth has a certain set of parameters, Wi-Fi has a certain risk. If you have infrared from old things, ultrasound, whatever you have to understand these values, right? And quite interesting because for these technical parameters, you have no impact. What you have an impact on is J. And if you can convince a lot of people to cooperate with you, this will have an impact. So is this beneficial or not? We will see in a minute. So here are some system parameters we used in our previous work. We also use it here in the lecture. These are values we looked at the energy measurements of certain mobile phones, Nokia devices at the time. We are currently redoing it for other devices here at the chair. And if you look at these values, they will not change so much. What will really change is this Z. So here we assume that a short range is 6 times faster than the cellular one, which nowadays is not really the case anymore because it's always a race, and cellular is continuously going better. And sometimes you get a new technology like Wi-Fi, AZ or whatever, and then you have a big jump. So this really is an interesting factor of the Z, while the others will not be so different, I would assume, if you have now a new mobile phone. So if we then look at the energy gain, then you will see that if you stand alone, it's 100%. There is no gain, of course. If you already have one partner you can cooperate with, you are already getting something like, I have to calculate this now, but I would say nearly 20% gain. And why not half of it right away? Of course, you have to invest energy in the sending and receiving. There's a lot of stuff involved. And if you want to see where the problem is, here you see that this darker green is the receive cellular, and the other one is send and receive on the short range. And the more cooperative partners you get, you will see that you will need less energy for the cellular one, which is clear because the more people are cooperating, the less you will get from the cellular part. And the less you also have to send out because you get less, you send out less, but you have to listen more and more proportionally on the short range to get the content. So in all cases, you get the same content. I hope this is clear. And you see the more devices you get to cooperate, the better it will become. But you also see it saturates, right? So I did not go farther than 10 devices because there's a trend. We also may have to discuss what happens to maintain such a cluster. And good cluster sizes are between 3 and 7, I would say, and then it will go up again, depending a little bit how you assume the mobility and others. But nevertheless, you get a big portion of the gain already if you have a few devices to cooperate, which is really good. And fewer devices also means less cost for maintaining the cluster. Maybe this is important. Okay, now you can even look at the gain in the time. So what is the time you will need if you cooperate, right? We know the time, this is TC, when you download it alone, and this is 1 over j TC is the time you're on the cellular, plus 1 over Z. This is the time you're on the short range compared to TC, because we are Z times faster. And we have to get the whole content over that over the short range, right? A part we send and the rest part we will receive. That is 100%. In the end, it's J over JZ, it's 1 over Z. And if you look at this, this is the delay curve, and you see with an even larger number of cooperation, the download time goes down. But now what you see here also interestingly is the time you spend on the cellular, which is really 100% if you're alone, 50% if you have one cooperating partner, 33%, and so on. It's 1 over j, right? This is the time you spend on the cellular. And then you see the other rest. Here you see two portions. Sending and receiving is the same, because we assume that receiving and sending data rate on the short range is the same. So here you will see that I'm sending something, I receive something. If I have two cooperating partners, only I have to send something and twice the time I'm listening to it. And with four times, one I'm sending and 3 times I will receive it, and so on, right? And you see also here the time I'm on the short range sending becomes slower or less, and the time I have to listen on the short range goes up a little bit. Okay, this was the part for the sequential case, right, which is really only having one error interface on. What happens if we can say I have two error interfaces on, right? And then it changed a little bit. If you assume that you don't have one big portion, but you now take the big portion from the cellular and you separate it in finer granularity, you need to get the first one, and then you can start the exchange, and at the same time you get the second part of the blue, so to speak. Okay, and if you go to a very small fraction here, then you will see that this portion is not so important anymore, because you have maybe thousands of these. Then it means it's really parallel, even though you have to receive a portion before you can send it out still, right? But this overlap we don't assume now. We're assuming really that we can do it at the same time, and assuming that you can cut your content into several very small things, this should be also easy to do. Good. What will change now? First thing is, I still assume the short range is faster, or very fast, I have to say. It's always faster, but very fast, and you will see what I mean by that. So now you get one part of from the cellular, right, in a certain time slot. We're looking at the time slot. And while you receive this, something on the short range will happen. And you will send out one of the things, exactly what you get here, or the time before better, but assume you can send out one content here on the short range, and you would like to receive j minus 1 over here. And then there's an idle time, right? So idle time we did not have before, because we only switched on one error interface at the time we really need it. Here we have it in parallel, and we have to invest on the idle time as well. And it will have an impact, as you will see later. So I assume that the whole exchange can be done before the next cellular time slot starts. And therefore we call it fast, right? The short range is really fast here. But it has to do not only with the data rate, it has also to do with the number of cooperative users, as you will see. Now, we say that this fraction, we say one content has a nominal time of 1. So as I have to get only 1 over j, because there are j people cooperating with me. So I make sure that over the cellular 1 over j will come, and therefore the timing is only 1 over j. Good. And the time this short range exchange will happen, it's the same content as before, but I am z times faster, right? And therefore this timing is 1 over z. Why is this? You can, so first of all I have to say, you see already when we talk about the fast short-range technology, we assume that 1 over j is larger or equal to 1 over z. That's important. Now, why is this 1 over z? Maybe this is a little bit harder to understand. Maybe it's easier to understand that this part, this was 1 over j. If I send z times faster, you will see that this is exactly 1 over jz. And as I have exactly j of these time slot, and you put a j on top of that, it's j divided by jz, and then it's 1 over z. Okay. Now the question, how big is this portion, right? And this is quite easy if you understand that the receiving block is j minus 1 divided by jz. And then you say, what is the rest? That's quite easy. If you don't look at these values, just look over 1 over j and 1 over z, and the ratio of this is here. This is 1 over j minus 1 over z. Right? So this makes sure that this is larger than 0. This is the time you are idle, this is the time you are sending, and this time is you are sending on the short range. And this is the time you are receiving on the cellular part. So we will do the same as we have done before. Now we say for our fast assumption, the time we will use there is 1 over j Tc, and the energy is 1 over j multiplied Tc PCR. So this is the one that comes from the cellular, right? So if you look at the short range, you will say I have a time I send, I have a time that I will receive, and a time I'm idle with the certain given power values. And then you just take the terms that we had before. It's 1 over j z Tc, and then j minus 1 over divided by jz, and here 1 divided by j minus 1 divided by z as one portion. Good. If you bring this all together, you have a cellular part now and 3 short-range parts. You can put this in, and I made it complete to say, and this is the second part here of the equation, there is no idle time involved on the cellular. This is important for later. I just put it here that you can find out what's going on. So 1 over j Tc is this time you will receive on the cellular. 1 divided by jz Tc is the time you have to send. J minus 1 divided by jz is the time you're receiving. And then idle time is 1 divided by j minus 1 divided by z. Okay, that seems to be easy. Why we have this differentiation with fast and slow, that I will show you here. There might be the time when we have so much activity ongoing, or z is not fast enough, that now the idle time is on the cellular reception and not on the short range, right? So this is a little bit different now. So let's have a look in this. This remains 1 over z. And here we have 1 over divided by jz for the sending, and j minus 1 jz. This is clear for the receiving part. This is still the same, but no idle time on the short range. On the other side, 1 over j is still the time I need to receive something, but now the idle time on the cellular link will change, and not surprisingly, this is now 1 divided by z minus 1 divided by j. Now 1 divided by j must be smaller, equal 1 over z. So that you see here. And then you can do the same here. You can look at the timing, how long it will take to do the exchange 1 over z, and the cooperative idle time, which we did not know. It's here. Cellular idle can be calculated like this. Good. We put this now into the overall equation, and then you see that we have 2 terms that are coming from the cellular, receiving and an idle, and only 2 parts or 2 meaningful parts from the short range. I also put you here the idle time with a 0 just for completeness. Okay, now if we look at the overall performance for this, you will see that you have similar results as before. Now I give you even the portion for the cellular receive and idle, and short range sending, receiving and idle, and you see how the energy goes down again as before. It seems a little bit different now. What you see here is that until you come to the point 6, that you always will find a little bit of idle, even though here's a 0 already. It's a rounding thing. It's still not 0. This is the time because Z is 6. Here is where we calculate the equation with the fast exchange, and here with the slow exchange. And then you see this is a differentiation, and this is, again, you see here, this part, you take this kind of equation as before. I just took this one where the idle time is already set to 0. On that side is then the fast one where the idle time of the cellular is set to 0. Okay, so also here you see the 0. There is a little bit, and it grows very slowly. So just that you know. Therefore, we had these two equations, right? Because if J goes up a little bit like this, then you see there's a differentiation. If you then look at the time, you see that we are going down until we reach the time Z, and then we will not improve anymore because due to the idle time, we just have to wait. And the short range will then do too much while the cellular link cannot gain anymore. Okay, so yeah, just another plot. While this is the cellular view, here you also have what happens on the short range, just for completeness. Okay, now we had a case of downloading the same content. What is about streaming? Streaming means live content. So we cannot just assume that we have all the content available. It will come with a constant bit rate from a server, and what will change in this example. So first we have we stream it again. We will send out the parts and look what happens. Now you see that the base station will send out some pieces, and one of the cooperative users will say, let me get one of them. So the blue will get the first part, just to correspond with the color, and then send it out right away. The red will do the same, send it out again. And while you send it out on the short range, the others over the short range will listen in for this. This is a little bit different than before, because what you see now is there are a lot of idle times that you as a user have, right? So now if you assume this is where the whole, over the time unit 1, the whole streaming content for a cooperative cluster with of size j will be disseminated. 1 over j is the one I'm really receiving. 1 minus 1 divided by j is the time I'm idle. And on the short range, I have now 1 over z activity with 1 divided by jz for sending, j minus 1 divided by jz for the receiving, and then the rest 1 minus 1 divided by z as idle time. And this will have a negative impact compared to the cases before, because we have way more idle time here. And if you now look at the streaming one, we don't have to make now the differentiation anymore. We can just say I have a part of receiving on the cellular, a part of being idle on the cellular, then a part of sending on the short range, a part of for the receiving on the short range, and a part for short range being idle. So if you look at this, then you see with more cooperating terminals, we get also a gain, but the gain is not as big. So I told you before, with the first cooperating partner in download, we had already 20%, more or less, right? A little bit less, but here you have only around 5% gain. And then with the third one, you get a big jump and then smaller jumps from there on. And this is for the energy. And if you look for the timing plot, there is no timing plot, because in the streaming case, we don't have a gain in the streaming use case, because whether you stand alone or if you're cooperating, you have to wait for the end of the sports transmission. You will not see it earlier than the others. That is clear. So if you look at the overall for the energy, then you see the streaming one is a little bit worse, than our sequential and parallel case, right? They differ a little bit here in the beginning, but this is more or less the same. Interesting is more the time event. As I said, the streaming one does not have a gain. It's always the nominal time. And here the parallel one is really outperforming the sequential one, right? Because here you will see a gain in doing that, which is clear. So these are some ideas for the cooperative cluster that you get a gain. And bear in mind, for example, here, if you look at the, if you go to the, to the energy again, if you say 50%, more or less here with four users in the cooperative cluster. So if you find 3 friends around you cooperating with you, you can already reduce the energy by half. And this is quite interesting. And this is something where you can really lure in the people into such a service. Okay, now let's continue with a new one, but in a minute.